This is the ocean, a vast expanse of forbidding waves and savage swells. It is home to the deadliest weather formations in the world. Here, two men risk their lives every day to save the planet's coastlines and inhabitants. They are the best in the business, a unique team called in to handle any crisis. Paul is a top cyclone chaser, specializing in nothing mundane and everything extraordinary. Simon is a world-renowned meteorologist and tsunami survivalist. They have been partners and friends for over 2 years, and together they find and film the greatest weather pattern seen on Earth. This is Meteorologist Corner.
Only a portion of the world's populations live near an active fault line or on new unstable slopes, but all are exposed to weather-related extremes, and severe storms account for 6 of the top 10 most expensive disasters recorded to date. The 2011 Atlantic hurricane season produced 20 tropical cyclones, 19 tropical storms, 7 hurricanes, and of these 4 major hurricanes. Hurricanes are also referred to as tropical cyclones, and typhoons depending on magnitude and location.
That's correct, Paul. Did you know that each year hundreds of storm systems spiral out from the tropical region surrounding the equator, but only 40 to 50 intensify enough or survive long enough to grow and become classed as a hurricane?
Each hemisphere also has its own hurricane season. The Northern Hemisphere lasts from June to November. The Southern Hemisphere starts in January until March.
That means 75% of the year, Paul, there's a chance of a hurricane. No wonder I never see you. The cyclones are classified by sustained wind speeds on the Saffir-Simpson's hurricane scale. Category 1 with a wind speed of 74 to 95 miles per hour. Category 2 with a wind speed of 96 to 110 miles per hour. Category 3 with a wind speed of 111 and 129 miles per hour. Category 4, wind speeds of 130 to 156 miles per hour. And ended on Category 5 with wind speeds above 157 miles per hour. So, I can hear you all asking, how are hurricanes created?
Well, let me tell you a little bit about Earth's atmosphere first. Earth's atmosphere is greatly influenced by gravity. Our atmosphere weighs a massive 4.99 quadrillion metric tons. The molecules closest to the Earth are compressed by the weight of the air above. These lower molecules are also the warmest.
Fact, atmospheric molecules are also mostly heated by land and sea, not the sun as is always assumed.
A good point, Simon. Back to where I was. As the heat increases, the molecules move further away from each other, decreasing the density. This heated air rises to higher altitudes where the molecules are less compressed by gravity and the above layers. As these molecules rise, the water vapour condenses to form storm clouds and rain droplets. The condensation releases heat called latent heat of condensation.
Time to get technical, Paul. Condensation in the atmosphere causes the temperature of a cloud to be warmer than it otherwise would have been if it did not release latent heat. Anytime a cloud is warmer than the surrounding environment air, it will continue to rise and develop. The more moisture a cloud contains, the more potential it has to release latent heat.
The process of condensation in turn heats the cool air below it, causing that to also rise. As the air rises through the atmosphere, it is replaced by the water surface by warm, humid air, which in turn continues the process of drawing more warm, moist air into the developing storm and moving that heat from the ocean surface into the atmosphere. So as the warm, low-pressure air rises and the cool, high-pressure air falls to replace it, a pressure gradient is created. This exchange in heat creates a pattern of wind that circulates around a centre called the eye of the storm.
As the rising air reinforces that which is already ascending from the surface, the circulation and wind speeds of storms increases. High-altitude winds, up to 9,000 metres above sea level, help to remove the rising hot air from the storm's centre, keeping the storm organised. The high-pressure air sucked into the low-pressure eye causes the wind speed to increase. So, what causes the hurricanes to spin?
Simple. Coriolis, which is the force that affects the rotation of the hurricane. This affects the northern and southern hemispheres differently, causing the hurricanes in the northern hemisphere to rotate counterclockwise and for their path to deflect to the right, and in the southern hemisphere to rotate clockwise and to deflect to the left.
So, let's go back through the key points for a successful hurricane.
The surface waters must be warm enough to actively give heat and moisture to the overlying atmosphere, needing temperatures of 26.7 degrees for 60 meters of depth. Atmospheric moisture from the seawater must condense to create excess energy, or a ready brewed storm passing over heated waters, with a location of around 5 to 20 degrees north or south of the equator to ensure a competent Coriolis force to create wind deflection, and a powerful but organised wind pattern.
At least we know it's possible to dissipate such a storm, Si.
That's true, Paul. A rapid decrease in intensity occurs when the cyclone is deprived of warm water needed to maintain its power. This can happen once it moves onto land, also known as landfall.
That's a fancy term for reaching land.
Certainly is, thank you, Paul. After landfall, most tropical cyclones become disorganised and become areas of low pressure within a few days, or evolve into extratropical cyclones.
Low pressure cyclones, less power, occur in the mid-latitudes of the Earth. Bit boring, not worth chasing.
Indeed, that's so, Paul, but don't forget the danger of storm surges, and I'm not talking about the transformer. Storm surges occur during landfall, primarily caused by high winds pushing on the ocean's surface. The pressure causes the water to overlay higher than the ordinary sea level, and combined with low pressure in the eye of the cyclone, topography of the land surface and the persistent wind can cause a high pressurized influx of water into the coastline. This, along with the rainstorms caused by the system, can cause massive flooding interactions.
I may be the only one hoping for climate change.
You certainly are.
It's predicted to have the effect of increasing the quantity and intensity of hurricanes due to excess heating of the seas and the higher atmospheric moisture content. Everyone else will be looking for houses further inland. So, Si, do you remember the filming we did for Hurricane Earl in 2010?
I most certainly do. A long-lived cyclone and the first major hurricane to threaten New England since 1991. He even reached sustained wind speeds of 140 miles per hour. Got a lovely video of it, didn't we, Paul?
We did.
Tsunamis have become increasingly common in recent years, and the science behind it is still in its infancy, Paul. It's been recorded that 80% of tsunamis occur in the Pacific Ocean, but can occur in any large body of water. Tsunamis used to be referred to as tidal waves, but however, we scientists declared that they had nothing to do with tides. Therefore, although they resemble the rise of tide, they are to be called tsunamis.
How picky. Tsunami is a series of water waves which are caused by the displacement of a large volume of body of water, typically an ocean or large lake. Many natural occurrences have the ability to create a tsunami, namely earthquakes, volcanic eruptions, landslides, glacier calvings, and meteorite impacts. Underwater landslides are called skarrocks. Waves arrive in wave trays, with wave heights increasing up to tens of metres in large events. Where the impact zones are largely contained to coastal areas, destruction can be extremely widespread and affect entire ocean basins.
I know that at the moment, plenty of research is being undertaken to see why some large earthquakes don't create tsunamis, whilst others with smaller quakes do.
And into understanding and mapping the tsunami paths and interactions with Pacific coastlines.
A good job too, Paul. Tsunamis have a small amplitude, wave height, offshore and a very long wavelength, often as long as 200 kilometres. Such a wave can travel at well over 500 miles per hour, which is why they can pass unnoticed at sea, forming only a swell of 30 centimetres above the normal sea surface.
It's not until they reach shallow water that they grow in height, mainly by the wave shoaling process.
Wave shoaling. Wave energy transport velocity decreases with a reduction of water depth. Carry on, Big Ball Paul.
Let's go, Simon. This wave shoaling compresses the wave and the speed decreases to below 50 miles per hour. The wavelength decreases to around 12 miles and the amplitude increases dramatically. Except for in the cases of the larger tsunamis, the wave does not break before reaching the coastline, creating the wall of water. Now think back to Ralph's lecture. It may be helpful. Tectonic earthquakes are associated with the Earth's crust and its convergent plates. When these earthquakes occur beneath the sea, the water above the fault line is displaced. Movement on all fault lines causes the displacement of sediments in the seabed. However, even the largest of these events is normally too small to give rise to a significant tsunami.
Storm surges, as mentioned earlier, can be called mega or meteor tsunamis. However, they are not classified as tsunamis. So, how do tsunamis cause damage? The main factors are the force of a wall of water travelling at high speed, hitting the coastline, and the destructive damage of water surging inshore and picking up and carrying everything it can.
Only a portion of the way.
Time to get sexual. As we ride in
Our atmosphere weighs a massive 4.99 quadrillion metric tons.
Your mum?